Good afternoon, Professor and our lab members. Thank you for taking the time to attend my master thesis defense. Today, I will present my research entitled Investigation of Atmospheric Gases in a Mixed Residential Industrial Area, Jeonju, South Korea. The using passive air sampler focusing on a spatial distribution, the source apportionment, secondary formation, and health risk. In this study, I investigated how viruses are distributed across the industrial, urban, and rural environment in Jeonju, and evaluate their potential environmental and health risk. The presentation is organized into 4 parts. The first is the introduction. The second is method. The third is the result and discussion. And finally, I will summarize the major finding and conclusion. The first, I briefly explain the target pollutants of this study. The volatile organic compounds, or VOCs. VOCs are organic compounds that can easily evaporate into the atmosphere, and they originated from the both anthropogenic and biogenic source. They are important because they can affect human health. In addition, the VOCs can participate in atmospheric reaction and contribute to the formation of secondary pollutants, such as the ozone and secondary air or secondary organic aerosol. According to the 2022 CAPS emission inventory, the VOCs account for the largest fraction of the air pollutant emission in Jeonju, representing about 55% of the total emissions shown here. When emissions were normalized by area, the Jeonju shows about 75,000 kilograms per square kilometer. This value is lower than the Seoul, but higher than the Ulsan, indicating that the Jeonju has a relatively high VOC emission density despite not being a large coastal industrial city. In Jeonju, the industrial activities are concentrated in a relatively compact area. Based on a source category distribution, the production process accounts for the largest fraction of VOC emissions. The followed solvent use and waste treatment. This suggests that emissions may be spatially concentrated near the industrial area rather than being evenly distributed across the city. Another important feature is the industrial, the residential, and green area are located close to one another. So emission from the industrial area may influence the nearby living environments. The geographical setting of the Jeonju may also influence the pollutant dispersion. The Jeonju is located inland and is surrounded by elevated terrain. Especially toward the eastern side, the under western or southwesterly wind condition, the surrounding mountain has the weakened air flow and promote the local stagnation over the urban area. Therefore, the VOC emitted from the industrial and urban source may accumulate more easily under certain meteorological conditions, which make the Jeonju an important area for spatial distribution monitoring. Although air pollution research in Korea has been actively conducted, the studies focusing specifically on Jeonju are relatively limited. The graph shows that the number of publications related to air pollution in Korea has been increased in recent years, whereas the number of studies related to Jeonju remains small. This indicates the regional research gap, especially considering the Jeonju has a relatively high VOC emission density and a mixed land use structure. For this reason, this study aimed to calculate the VOC pollution in Jeonju. The passive air samples were used during summer, fall, and winter. The target VOCs were analyzed by GCMS. Based on this data, I evaluate the spatial and seasonal distribution to identify the major source factors using PMF, the calculated secondary formation potential, and assess the health risk. The final goal was to provide the basic information for managing toxic and reactive VOC in Jeonju. For sampling, I used the Ladello passive air samplers. The passive air samplers do not require electricity, which make them easy to install and useful for collection spatial distributed data. They are also cost-effective, so multiple sites can be monitored at the same time. This advantage made it suitable for investigating VOC spatial patterns in Jeonju. The 15 sampling sites were selected around the Jeonju industrial area. They were classified into three groups, an urban and industrial and rural site. The map also shows the population density and highway and the boundary of the industrial area. A key feature of the study domain is the close proximity between the industrial facility and residential or rural area. Therefore, the site network were designed to evaluate not only concentration inside the industrial area, but also the possible influence the surrounding living environment. The sampling was conducted in the 3 seasons. The regional plan focused on the summer and winter, but the fall was added to better capture to transition between the warm and cold season. After sampling, the VOC absorbed on the cartridge were extracted using the carbon distal pipe. The instrumental analysis was performed using a GCMS. The detailed conditions are listed on the right side of this slide, so I will not describe each parameter in detail. The target list includes the 53 VOC species from the M502AL standard. These standards include the aromatic hydrocarbons and halogenated and several the hazardous air pollutants. The L risk indicate compounds that are also include the Korean Health Monitoring Network, except for the 1,3-cation and vinyl chloride. Many of these target compounds are important for health risk assessment because they include the carcinogenic or toxic VOCs. The QA/QC of the data was evaluated based on the R-square value of the calibration curve and MDS and recovery rates, all of which are within the acceptable range for analysis. The several programs were used for the data analysis, basic statistics and statistical tests performed using SPSS and SIGINT-PLOT. The ArcGIS was used to visualize the spatial distribution of the VOC concentrations and related indicators. The PMF model was used for the source apportionment, and for health risk assessment, I used the AirQ Plus framework and Crystal Ball for the Monte Carlo simulation. These tools allowed us to evaluate the data from the concentration level to source and potential health impacts. To quantitatively identify the source factors, I applied the PMF model. The 19 VOC species were selected as input compounds after considering detection frequency and data quality. The compounds with a detection rate of the 20% or lower were excluded. For concentration below the MDL, 1/2 of the MDL was used. The uncertainty was calculated using the equation shown on this slide. For value below the MDL, the uncertainty was set to 5/6 of the MDL, while the detected value was assigned uncertainty based on concentration and MDL. The secondary formation potential of the VOCs was evaluated in 2 ways. The first, ozone-related reactivity was estimated using the propylene equivalent approach, which compared the OH reaction rate of each VOC with the propylene. This helped evaluate the relative photochemical reactivity of the different VOC species. The second, the secondary organic aerosol formation potential, or SOAFV, was calculated using a SOA yield method. In this approach, the concentration of each VOC is multiplied by the yield value to estimate its potential contribution to secondary aerosol formation. For the inhalation risk assessment, the both carcinogenic and non-carcinogenic risk were calculated. The major input parameters include the exposure concentration, the duration, the frequency, time, and averaging time. The most exposure factor were based on the US EPA recommendations. However, the exposure time was adjusted to better represent the realistic outdoor exposure in Korea by combining the average outdoor time of the Korean population with the occupational exposure time. This approach was used to evaluate a practical exposure scenario for residential and worker around the industrial area. To account for the uncertainty and variability in the exposure assessment, the Monte Carlo simulation was performed. Instead of treating all the exposure variable as a fixed single value, the simulation allowed the selected parameter to vary within the defined distributions. This approach provides a range of the possible risk values rather than not only deterministic estimate. In this study, the number of the simulation trial was set to 10,000. The results were then used to evaluate the risk distribution for different exposed groups. In addition to the direct inhalation health risk, I also attempt an indirect evaluation of the potential health burden related to the secondary formation. For this purpose, the ARQ+ framework developed by WHO was applied. The calculation required the pollutant concentration, the baseline, the mortality rate, and the exposed population. In this study, the SOAFV and OFV were used as a proxy indicator for secondary PM2.5 and ozone-related potential. Therefore, the result should be not interpreted as an actual mortality estimate, but rather than a screening level comparison for potential health burden associated with the VOC's secondary formation. Now, I will present the result. The seasonal average concentration of the total 53 VOCs was lowest in summer, followed by the fall and winter. The average concentration was 3.4 microgram per cubic meter in summer, the 6.6 in fall, and 8.2 in winter. Although the winter mean was higher than the fall mean, the difference was not statistically significant. This is because the winter average was strongly influenced by the one high concentration hotspot, rather than a uniform increase across the whole city. Therefore, the fall and winter shows the similar overall concentration level, while the winter had a stronger local hotspot effect. The concentration level in Jeonju were also compared with those from other projects. Based on the ANOVA test, Jeonju was statistically different from not statistically different from Cheongju, Daesan, Pohang, and Yeosu. This is the yellow bar. This suggests that the VOC concentration level in Jeonju can be comparable to some area with larger industrial complexes. Although difference in sampling period and site characteristic should be considered. Another notable feature is that the concentration of the variability in Jeonju was as large as in some other industrial area. The comparable composition was dominated by aromatic hydrocarbons. The VTEs account for about 80% of the total VSC concentration. The toluene alone contributed approximately 40%. And this indicates that the Jeonju VOC composition was strongly controlled by a limited number of aromatic hydrocarbons. Because the sampling sites were located near industrial, urban, and rural environment, these VTX compounds rightly reflect the combining influence from solvent use, industrial activity, and fuel-related emission and traffic. Therefore, the VTX can be considered as a key compounds group for understanding VOC pollutant in Jeonju. The spatial distribution shows here average concentration around the industrial complex. In particular, the elevated concentration of field near the industrial site and some sites located downwind and adjuncts to the industrial area. This pattern suggests that the industrial complexes may be an important source reason of VOCs in Jeonju. The influence may be related to production processes and solvent use and coating, adhesive, and other manufacturing related activity. However, because the study included the mixed land use, the observed the spatial pattern should be interpreted as the combining effect of the industrial emission near urban source and local meteorological condition. For source apportionment, the appropriate number of the PMF factor was examined. The Q over Q value increased as the number of the factor increased. The three-factor solution provides a reasonable balance between the statistical and performance and interpretable. So, to support this decision, NMF was also applied, and it also indicates that the three-factor were appropriate. And therefore, the final PMF solution was selected as a three-factor. And these factors were interpreted based on the chemical profile, the seasonal behavior, and spatial distribution. The three PMF factors were interpreted as follows. The factor 1 was associated with the solvent use, the fuel handling, and evaporation. This factor had a high contribution from the 3-methylbenzene and para-isopropyl solvent, which can be related to gasoline-related evaporation, the solvent, and mixed urban sources. The factor second was interpreted as an industrial activity factor with strong contribution from toluene, ethylbenzene, and xylene, which all commonly relate to paint, coating, and adhesive, and industrial solvent use. The factor 3 was interpreted as a combustion and heating influence, because the benzene and some chlorinated compounds contributed to this factor, and its contribution increased in winter. The factor contribution by the site and season also supported this interpretation. The factor 1 increased during the summer, which is consistent with enhanced evaporation under high temperature conditions. The factor 3 increased during the winter, suggesting strong effect of the combustion or heating-related source in the cold season. In contrast, the factor 2 remained relatively consistent all across the season. This industrial-related factor appeared not only the industrial site, but also the nearby industrial activity may be expanded beyond the industrial end itself. The diagnostic ratio were used as a supporting evidence for the PMF interpretation. The y-axis represents the ratio of the MP-xylene to ethylbenzene, which can indicate the relatively importance of the local and transported influence because the xylene are more reactive than the ethylbenzene. Except for some industrial site, the left dot one, the y-axis value were relatively similar, suggesting that many sites were influenced by similar source conditions. And the x-axis were used to distinguish industrial and traffic-related influence. Overall, the industrial site was located toward the industrial influence side, is the right side, supporting that the interpretation that the sampling domains was broadly affected by the industrial area. The seasonal OFB distribution showed a pattern similar to the total VOC concentration. The OFB was generally high around the industrial complexes, and the major contributors were toluene, MP-xylene, and 1,2,4-3-methylbenzene. These compounds are important because they have both relatively high concentration and strong photochemical reactivity. The OFB also tend to increase from the summer to winter, following the concentration trend. The sun ruler site shows a locally high value, which may be associated with a nearby the fuel-related or the solvent-related source, especially 1,2,4-trimethylbenzene. The SOAFE's distribution was generally similar to the OFE pattern, with a higher value around the industrial complex. However, the compound's contribution were somewhat different. The toluene, benzene, and ethylbenzene were the main contributor to SOAFE. In particular, the benzene became more important in winter because of its relatively high concentration and high SOA yield value used in the calculation. Therefore, the winter SOAFE was strongly influenced by benzene. For the direct inhalation risk, the overall mean concentration was used rather than seasonal value. Because the chronic risk assessment is based on the long-term exposure, the spatial pattern of the risk was partly similar to the secondary formation region, but the variation among the sites was relatively small. For example, the coefficient of the variation for concentration was about 65%, whereas the CV value for the chronic carcinogenic and non-carcinogenic risk were much more lower. The value is the cancer is 8% and the non-cancer is 15%. This means that from health risk perspective, the exposure level were relatively similar across the industrial, urban, and rural sites, suggesting that the VOC exposed may be regional issues rather than the problem limited to the single hotspot. To indirectly evaluate the health burden of the secondary formation, the ALQ plus was applied using SOAFE and OFE as a proxy concentration indicator. The calculation estimated the SOAFE corresponding to potential mortality burden of about 23 deaths in Jeonju, while the OFE corresponded to about 7.7 deaths in Jeonju. However, these values should be interpreted very carefully because the SOAFE and OFE were treated as if they were actual PM2.5 and ozone concentration. So atmospheric formation and dispersion and removal and the chemical transformation process were not fully represented. Therefore, these results indicate a potential health burden, not a definitive estimate of actual deaths. So finally, I will now summarize the main conclusion. First, the VOC concentration in Jeonju generally high in cold season and the near industrial area. The BGS was the dominant VOC group, indicating that the aromatic hydrocarbons were key indicator of the VOC pollution in this region. Second, the PMF identified the three major source factors. The first is the evaporation-related source. Second is industrial activity. The final is the combustion and heating-related source. The industrial-related influence was not limited to the industrial area, but also many extended to adjacent residential and rural area. The third, OFE and SOAFE were mainly driven by the aromatic VOCs. And direct health risk did not exceed the guideline level. However, there was little difference across all sites. Overall, the VOC management in the Jeonju should be prioritize the toxic and reactive aromatic hydrocarbon and consider the industrial area and near residential zone as a one connected exposure area. This is my end of page. Thank you for your listening.